We're going to start chapter 2 today. And chapter 2 is where the calculus starts happening, except the first section is not really going to be calculus. It starts at section 2.2, but 3.1, we're going to talk about measuring change. Rates of change. This is going to be very short because there's really only one thing we care about in this section, and that's going to be your average rate of change. So let's say we're given a function. Does anyone know what we use to describe the average rate of change? The formula to compute it? Yeah?
F of B minus F of J over J.
Yep. Who's that guy? What do we call that? We have a name for that. Alright, that's the difference quotient. Okay, so this is a quantity that measures how a function changes on average over some interval. Okay, so we can imagine our function is doing whatever, but we're only concerned about on the interval a and b. What is the function doing on that interval? Not specifically at every single point, but overall. Notice that if here my x is a, this would be f of a. And this would be f of b. And I care about how this function changes overall. So I don't care about what happens on the inside, I care about on average what's happening. Overall, how is this function changing? And it turns out that we can use a slope formula. This is y1, if this is x1, and that's x2. We can use y2 minus y1 over x2 minus x1, and we end up with this formula. And this here tells us the slope of the line connecting these 2 points. Or one way you can think of the slope is it tells you how much you move up or down when you move 1 unit to the right. Right? So it's like for every 1 unit that we move over in the x, how much is our y value changing? That tells you how it's changing on average. So that's the most common way to describe this quantity, but it's of course equivalent to another way that I mentioned before. But it's equivalent to something else that we know about. The other form for a difference quotient, which is f of x plus h minus f of x all over h. Right? And really this one, to get from that one to this one, it's really just a change of perspective. Here h is not concerned with a particular x values, b and a. It's concerned with the distance between the x values. So you can imagine take the same kind of idea, except here call the first value x. If we move a distance h to get to the next value, which I call x plus h, and do the same thing. Now this here is f of x plus h. This here is f of x. And so if I do y2 minus y1 over x2 minus x1, I end up with this formula. Right? So it's actually equivalent to this formula. However, in this context, this is the most common way to express it. There are other contexts in which this is the common way to express it. But when we're talking about average rate of change, this is the way we're going to use, because we're usually going to be given these 2 specific x values. And so it's just nice to have a formula that has those x values that you're going to plug in. You want to remember that a is the limit, the left x limit, and b is the right. Right, so the smaller one, the bigger one, and you do it in that order. So one kind of question I would ask here, and so it's sort of going to be asked in this form. Is I'll give you a function, and I'll ask you to find the average rate of change of that function. So example, find the average rate of change of f of x equals x squared plus 1 on 1, 4. Right, so that would be an example of a typical question, and they're really not going to get more complicated than that, actually. There's not going to be some huge word problem here. It's usually going to be stated something like this. The difference is how the interval is stated might change, but it'll mean all the same thing for you to understand what intervals mean. So this we might say as something like from x equals 1 to x equals 4. Or we might say on x from 1 to 4, or we might say something like from the point where x equals 1 to point where x equals 4, or something similar like that. So there are a multitude of ways I can phrase asking about a particular interval. I can phrase it several different ways, but at the end of the day, when I ask you to find the average rate of change of a function, I'm going to give you a function and I'm going to give you an interval, and you need to know how to pick out the parts. So once you have this interval, you always remember that a is going to be the smaller x value and your b is going to be the larger x value. So now, you can actually do this problem. So you can say the average rate of change is, what's going to be here?
F4
F of 4
minus F of 1 over 4 minus 1.
Exactly. Just plug into the formula. Which, if you don't remember the formula, although by now you should, but in general, there's a formula that you'll need to memorize, and I do require you to memorize this formula, is every time you're doing a problem that needs that formula, you write the general formula down, and then you start plugging stuff into that formula. And so, what would f of 4 look like?
17.
Give me the steps.
4 squared plus 1, so 16 plus 1, so that's 17, minus 1 squared plus 1, and that's all in parentheses.
Right, parentheses, very important.
Yeah.
All over.
All over 3.
4 minus 1, which is 3. So this just becomes basically 15 over 3, or 5. And so we can say the average rate of change of this function on that interval is 5. And that basically is to say, on this interval, on average, every time the x value moves over 1 unit, the y value will move up 5 units. Up is specifically by the plus 5, is the idea that we're moving. So that tells you your y value is increasing. If the function was going down, it would be decreasing. And you can look at what this function here is doing. Right, so that's your function x squared plus 1. Here's, I can plug in a 1 here and a 4 here. So 1 starts at 2. This guy starts at 17. You'll notice that the difference between 2 and 17 is 15. So overall, your y values change by 15 points. But in relation to the x, they change by 15 points during the same period that the x values change by 3 points. So every time you moved to another point, your y value increased by 5. It would have been 7 here, and then it would have jumped by 5 again. So you can manage on average. These might not be the exact points, depending on the function that you're talking about, but the idea is on average, how much is your y value changing? right? So you can expect it to be jumping by roughly 5 points for every one x unit. And that's kind of what this function is a measure of. Not necessarily what's going on in the interim, but what's going on overall on average in a straight shot from here to here. That's kind of the idea. Now sometimes that idea is useful, and we will actually use that idea and come up with some useful results later on. But that's basically the idea. Any questions on that? So yeah, sometimes you care about the average. We will specifically be using this idea to develop some more sophisticated things later on. But sometimes you just care about how something changes on average, or as opposed to how it's specifically changing at some specific point. Okay. That's it for 2.1. There's not much to do here. So it talks about rates of changes and slopes and all that stuff again, but we actually discussed that in a little bit before, and we'll discuss it again. So I don't think there's any point in discussing it in 2.1. The main thing that I wanted to start here today is actually 2.2. We're going to start limits. Now this is a much longer section. We won't get it done this class, and we probably won't get it done next class either. But it's a very, very, very important topic. And that is the topic of limits. Now, different math disciplines study different things. Now, if you were to ask someone, what is calculus? What is that the study of? A one-sentence answer would probably be something like, it's the study of derivatives, integrals, and their applications. That is a nice, concise one-sentence definition of calculus, right? So those things, derivatives and integrals, I didn't tell you what those are yet, so if you don't understand what those are yet, don't worry about it. However, if you were to force someone to say in one word, you only have one word to tell me what calculus is about, the answer would be limits. Because your derivatives and your integrals are in fact defined as limits. They are the foundation of everything calculus is based on the idea of a limit. And it's a very important idea. It's a very sort of nuanced idea. In fact, I'm not going to tell you the specific definition of a limit because it's kind of outside the scope of this class. I'll give you sort of a fuzzy working definition of a limit, and we will take it from there. But it's a very, very important idea, and it doesn't get its due justice in any standard Calculus 1 course, but limits are a very important idea, to say the least. So let's jump to the fuzzy definition of what a limit is. So given a function f of x we limit as x approaches a, some number a, of f of x is the y value. F of x approaches as x approaches a. The limit of a function is the y value the function approaches as the x value approaches some other predetermined number. Okay, so a few things to point out here is that this sentence is a very common sentence. In fact, we'll be able to write limits down very concisely, but usually I would say the limit as x approaches a of blah. Right, that's kind of how you talk about it. Other important words in this sentence, actually, the word the is pretty important. Okay? There is going to be the idea of a uniqueness to our answer, right? You want to almost even think of limits as a function. You put a function in to tell me some inputs, and it spits out a number that tells me what the y value is getting close to. Other important words in this is actually the words approach, right? And it's important when you're talking about limits that you really think in terms of approaching something or getting close to something. Actually being in the position is less important. In fact, it's completely irrelevant when you're talking about limits. You don't care about being somewhere, you care about getting close to somewhere. And that's why it's a very nuanced idea. And that's why I have to give you a very fuzzy definition. Because, you know, math people don't like these vague terms. What do you mean getting close? What's close? You mean 1 unit away, half a unit away? It's a very vague term. So math people came up with a way to actually specifically define the word close so that literally anyone can agree on what close is. How close is close enough. But we won't be getting there. So the idea I want you to take away is, you want to see what is the y value getting close to when your x value is getting close to some other number, right? And if you can determine such a y value, you call that y value the limit. Notation is the following. You write LIM. Underneath it, we write x with a little arrow, and we write the number that we want to approach. We want the x value to get close to the number a, and we write f of x right beside it. If your f has several terms, you can put parentheses here, but if it's just like one compact thing, it's customary to just write it down right beside it. So this is saying the limit as x approaches a of this function. And the answer, when you're thinking about that, what is that? What does this actually mean? Is the y value we get close to. Well, the y value we get close to. So basically your x value is doing something, and you're watching what the y values are doing at the same time. And you don't necessarily care about getting to a certain destination. It's the journey that matters, getting close to something. So let's jump into some examples. You have like 20 seconds left.
Well, I was just doing bonuses.
Huh?
I was just doing bonuses.
Okay, well, you have like 20 seconds left to do that. Okay, so, yeah, let's do an example. So let's say something like, normally I draw a bunch of pictures and do a lot of hand waving, but I did this with the last class, and so I kind of want to jump into some specific examples and learn about these concepts while looking at specific functions. So let's say I looked at something like x approaches 1 of the function x plus 1. And I want to talk about what is that, right? What is the answer? Now Victor claims the answer is 2. Is Victor correct? Well, let's actually kind of think about this from the definitions point of view. There are a couple strategies. I'll probably wait for the strategies until the second example, because there's something here that won't necessarily apply. Let's say we actually looked at the picture. We know that y equals x plus 1 looks like this. And now we realize that we care about the x value 1. And the question is, when we're getting close to that, what is the y value getting close to? The answer seems to be clearly 2. Because obviously you can plug 1 into this and just get 2 as the answer. But it's very important that you think of it in terms of actually getting close to something. When your x values get close to 1, your y values will zoom in on the number 2, right? So you'll say, as x gets close to 1, we have y gets close to 2. In fact, you can literally be at 1, and you can plug in 1, and the y value will output 2. But this is not always the case. This is actually just a special case of that idea. So we can actually say the limit as this approaches 1 of x plus 1 is 2. And I can write down that this is equal to 2, right? And that's because as I'm getting close to 1, I can be even plugging in numbers, getting closer and closer to 1 to figure out what it is. I can plug in, 0.9, 0.99, 0.999, 0.99999, 0.99999. Just keep plugging in numbers closer and closer to 1. And I'm inching and inching closer to 1, and then I'm looking at the y values and looking what they're approaching. And this would be approaching 1.9. 1.999, 1.999, 1.999, right? And it'll keep getting closer and closer to 2. Right? Here's another example. So that would be the answer here. The limit is 2. Let's look at another example. Again, we're approaching 1. Well, we're approaching 1 of this function. And now at this point we have a little hiccup because clearly, unlike here, I can't actually plug in 1 here. So ideas, what do you think the answer is? Yeah?
We can factor the expression on top. So x squared minus 1.
Yeah.
In fact-
So that's one idea you might have. You can think of that x squared minus 1, that's the difference of squares. And I happen to know that, hey, there's an x minus 1 hidden there somewhere. And so you can get away with doing that. So let's actually do that. So here, this one I can talk about some strategies, which I will summarize at the end of the chapter, but I think I just want to get you guys already used to looking at things in this way. There are some strategies, and you can just, one would be to plug in values of x actually getting closer to 1. So let's say this function was completely unfamiliar to you, you completely were unfamiliar with the idea of factoring, but you're still going by the definition of what a limit is. You can say something like, okay, here are my x values, here are my y values. Here's the number 1, which I can't actually plug in, so I don't know what the hell that would give me. But I can start plugging in numbers getting close to 1. So I can start with 0.9 and 0.99 and 0.999, right? And I can see as my x values are getting close to this, what are these y values getting close to? Are they approaching some number, right? And you can approach from the other side, like 0.1, 1.01, 1.001, 1.0001, right? And I'm approaching that way, and then I see what my y values are approaching as I go from either direction. And the idea is being that there will be some number that you're zooming in on, right? Possibly, not necessarily. But if there is such a number, that's the number you care about. This is one strategy. Of course, it's a very inefficient strategy for this class. Usually you won't use that. But it could be something that gives you some ideas. And it might help you in some of the homework problems. Another strategy is to actually, again, well, do as he said and factor. Notice that the limit of this guy here is equal to, I can factor this, so let's just do that. So that would factor as that. So I could say, for example, because the limit only cares about being close to something, we're not actually at the value 1, we're close to 1. So this number is a number other than 0. And this number is a number other than 0. So I just have a fraction of two numbers that are not 0 being divided. I can actually cancel them. Right? Because as long as I'm not at the number 1, I can cancel. It's just a regular fraction at that point. Okay? And so what happens is this will become the limit as x approaches 1 of the number of the function x plus 1. So it turns out the limit of this function is equal to the limit of that function, and we actually already know that the limit of this is 2. Here's another way we could look at it. Right, so we've reduced worrying about this function, which is complicated, to worrying about this function, which is a lot simpler to see the idea. In a similar way, 3, we could have actually graphed. We could have looked at the graph. So we could plug in values as we're approaching 1. We could simplify. I don't know if the camera's going to catch that up. We could have simplified to get that. Another thing is we could look at the graph of the function. And believe it or not, the graph of this function would look like this. It would look like a straight line, except right there you'll have a hole. And hold is a technical term, it's literally called the hold. I'm not just saying it's a hold, it's called a hold. That's a technical jargon for it. So at 1, you actually don't have a value, right? So there is no y value here. Okay? However, as long as we're not at 1, as long as we're on either side, this thing is just a fraction that I can reduce. I can reduce this fraction and I can get a number. And at all of the points I can reduce to get the number x plus 1. So other than at this point here where we divide by 0 and so it's impossible to actually calculate a value, at all other points the values are give the same output as the function x plus 1. And so the graph of this function is actually a straight line with a hole where the 1 should be. And so now you can take the idea of a limit. Now you can look at what is my y value getting close to. So there is actually no y value here, but if there were a y value, if I had to fill one in, what would that y value be? And so you can start to get close to 1 on the x, and then you track the y value. So you start seeing what is it getting close to. As you approach this number, you'll notice that all your y values seem to be closing in on some number. And I can approach all my x values from this side, similar to what I was doing with the table here. And so I'm approaching this, and then I'm watching what are my y values are approaching. And in this case, you'll see that both the y values are zooming in on a number, and that number happens to be the number 2. So you can graphically look at this. But the importance of this example is for you to realize that the function doesn't have to be even defined at the point where you're taking a limit, and a limit could make sense. The function itself doesn't make sense when x equals 1, but the limit makes sense when x equals 1. The limit actually gives you the output 2, while the function has no output. Right? So it's possible even if a function is not around for a limit to exist, which is why that idea of you need to think in terms of getting close to something, not necessarily plugging in something. So there are a couple ways you can get to the fact that this limit is equal to 2. So it's actually 2. That would be your answer. Now, not all strategies are created equal. There are some strategies that you'll use at different times, and I'll really summarize this when we get to it. But I just want you to know the kind of options that are available to you. Okay, let's look at another function. And let's approach 1 again. It's a function we've seen before. I did this example when we were doing piecewise functions. Let's say it was 1 when x is between 0 and 1, and it's x plus 1 when x is greater than 1. And the question is, what is the limit as x approaches 1 of the function of x? What do you think the answer is?
Would it be a positive and a negative? If for produce.
Well, no, I'm just talking about the limit. What's the answer for the limit? What is the y value this function will approach when my x value approaches the number 1? Why do you think it'll be 1? Whoever said that, I wasn't looking. Who said that? Why do you think it will be 1? Well, let's actually do some analysis here. I picked this graph because I want you guys to remember how to graph piecewise functions. So let's actually draw a picture here, use the third strategy, and see what do we think the answer should be. So how do we graph this? Someone remind me, what steps would we go through? What do we do here? How do you graph this function? Yeah.
So for every value including 0 and 1 for your x, would be just a straight horizontal line at y equals 1.
Right, so we know y equals 1 is just a horizontal line like that passing through 1, but we only care about between 0 and 1, so we ignore this side and we ignore that side, and we fill in the endpoints. Right? If you plug in 0 into this function, the output is 1. Plug in 1 into this function, the output is 1. And so on my picture, it looks like this. and that's filled in, that's the number 1, the x value is 1. Okay, and then what?
The other one would be,
Well, the same idea. What does y equals x plus 1 look like? Well, we've used that example multiple times at this point. It's just a straight line that has y-intercept 1 and slope is 1. But we don't care about everything because it's a piecewise function, so we only care about the part that's not including 1, but everything bigger than that, so the right side. And we ignore the left side. And so, if this value were included, what would it have been? It would have been a 2. And so I know at this point I'm going to draw an open circle in the y position 2, and then I'm going to draw that graph going like that. Okay, so now answer the question. What is the limit as x approaches 1? Anyone, take a shot at it. Yeah?
There's no limit
Why did you say there's no limit?
because they should go from both sides. I don't know. Like, the two.
Yeah, but we're 1 here.
does it depend what side you're coming from?
Well, let's say it doesn't. How would we have done it? Let's say we're coming from this side. What would the answer be?
1,
1. Let's say we're coming from the other side. What would the answer be?
2.
The answer would be 2. Now remember, we don't care about actually being there. We just care about what the y value is getting close to. However, this is the other part of the definition where I said the was important in the definition. There has to be a unique y value. Here it seems like we have 2 answers. There's one situation in which, okay, if I approach 1, the output is 1. But another situation when I approach 1, the output is 2. 1 is of course not equal to 2. These are 2 distinct values. We don't have a unique output, and so we say the limit does not exist. So we say the limit of x here, f of x here, is undefined. A more common term would be does not exist. I'll talk about the existence of in a little bit. And that is usually abbreviated with uppercase D and so you could write the limit here, limit as x approaches 1 of f of x is dne. Right? And that means does not exist. Right? Because there is no unique y value. However, it does bring up a certain point here that it seems that we could get a value that is meaningful in some context, and so that brings us to the idea of a one-sided limit. So there are things called one-sided limits, because you can see, it would appear that we could get an answer if we only cared about one side. So in terms of 1, there's the left side, and then there's the right side. So you can approach 1 from the left side, or you can approach 1 from the right side, and individually these two will give you an answer. They won't give you the same answer, and so our definition for an overall limit breaks, but our definition for a one-sided limit is going to account for this sort of situation. So we have these two guys. There's the limit, and I'm going to introduce to you the notation as well. So you write a and you write a little minus sign as a superscript of f of x. And this is called the limit as x approaches 1, or a, from the left. Okay. So that's only worried about one side, or it's called the left-handed limit. So here I can take the left-handed limit, and it would be 1 is the answer. There's also another notation where you put a little plus sign as a superscript, and that actually denotes the limit as x approaches a from the right. This is called the right-handed limit. So the left accounts for the situation when you're getting close to your number from numbers that are smaller than it and slowly increasing towards it, while the right covers the situation that you're larger than this number and you're decreasing towards it, but you're getting close to it from either side. And so in the above example, we could have the limit as x approaches 1 from the left of f of x, that was the number 1, and the limit as x approaches 1 from the right of f of x, that was actually the number 2. Okay, so the one-sided limits are fine, they can exist. The overall limit did not exist though, and that should be something we should probably know. Talk about the existence of limits. Yes?
For the example we just did, is there a way to find the answer without knowing it? Or is that
Yes, but I'll come back to that later. For now, I just want you to start. There are a lot of ideas and a lot of ways I want you to look at a problem, and I'm just exploring some of the ways you do right now. But at the end of the day, I will talk about some specific examples. There are situations in which it would be preferable for you to graph. There are situations in which it's not preferable. And there might be situations where it's preferable to simplify. There are situations where it's not, et cetera, et cetera. So at the end of this, right now I just want to introduce the ideas and strategies to you and kind of get you used to the concept, because for some of you, I think it's the first time you're seeing the limits. So we're just playing around with it right now. But I'll give you a concise summary of, okay, faced with a limit, here's what you do. Here's what you look for. Here's how you solve the different cases. But I just want you to get used to the idea at this point. So here, the limit only exists if both the limit as we approach from the left of f of x exists and the limit as we approach from the right of f of x exists, and they must be equal. They must connect. The limits must be the same. And this ties into a bigger idea that's called continuity of a function, and we'll talk about that later as well. And that's later in chapter 2. I don't remember when we talk about that, but we'll talk about continuity a little bit. Okay, so yeah, so that will be when a limit exists overall. Okay, so that's one way you can talk about a limit. So it's possible for limits to not exist. One thing I want you to note here, it's not always the case that you can find individual answers for the one-sided limits so that you can determine what the overall limit is doing. Sometimes even these one-sided limits might not exist. That's a situation that you have to worry about. Anyone think they can give me an example based on what we know a limit is? We have to get close to a certain value, see what the y value is doing. How can that not work if you only care about one side or something?
I don't know. I don't know, maybe if it's like x equals 2, like, never mind.
Well, x equals 2 is not a function in general, so that kind of wouldn't work. But I think you're kind of thinking along the same lines. If you had to have something like x equals 2, technically you can't get close to it from the right or the left. Can you kind of expand on that idea with a function as an example? Can you give me some function and some kind of limit that won't exist on that function even if you're taking one side? Yeah?
Like, say 1 over radical x. I mean 1 over x.
1 over x, okay.
From either side it won't exist. Or even from one side actually. It will never touch 0.
Almost, not quite. It won't give you a number, but in this class we will consider infinity as an answer for limits. I'm going to talk about that as the next section. But you're almost there. It's a close. But yes, the limit as 1 over x as x approaches 0 does not exist, but the one-sided limits we can define to exist. We can define the left side to be negative infinity while the right side equals positive infinity, and those two don't connect. How about something like y equals the square root of x? Look at that function. That looks like this. So now let's consider the question, what is the limit as x approaches -1 of this function? -1 is over here. There is nothing over there, right? It doesn't matter if I'm coming from the left or the right or I'm looking in general, there's literally nothing to approach, right? The function doesn't even exist there. So it is possible, so here none of the limits exist. Right? So you can't go approach from the right or the left. There's nothing to approach on. There's nothing to be on. Right? You can only take that idea over here. If you actually want the limit as x approaches 0, right, meaning right here at this point, the left-handed limit doesn't exist, but the right-handed one does. Right? And the overall limit wouldn't exist. The overall limit will only exist if you're away from 0. So this is an example where you can have all sorts of things happening. Right? So for all negative x values, none of the limits exist. Not the overall, not the left hand, not the right hand. For the value x equals 0, the left hand doesn't exist because you can't approach it from the left. There's nothing to approach. But the right hand does exist and it actually equals 0, so the overall doesn't exist. For any other number in the interior, the left and the right will both exist and they will connect to the value square root of the x value. So on one hand, I don't want to scare you guys thinking it's complicated, but I do want you to appreciate there are nuances to it. It's not just like plugging into an equation or something like that. You have to consider where something makes sense, where it doesn't make sense, what the behavior is from one side or the other side, what is it getting close to, whether or not the function exists or not at the point is irrelevant, so you just want to care about inching towards something. All of these are important concepts when you're talking about limits. So some notes here, limits need not exist. It is possible for any or all of limit as x approaches a of f of x, limit as x approaches a from the left of f of x, limit as x approaches a from the right of f of x to not exist. To not be able to give you a y value answer that makes sense in terms of our definition. Another thing you want to remember is that a limit might exist even if a function is undefined. Right? I did that example of x squared minus 1 divided by x minus 1 was such an example. It was not defined at x equals 1, but the limit existed at x equals 1. And the takeaway from that is limits care about getting close, right? You don't actually have to be at the point where something bad happens, like division by 0. you want to see what is the y value doing when you get close to such a point. So those are some or two main takeaways that you should take away so far. We'll end on one other concept, and we'll explore these and more concepts later on. And we'll start talking about the algebraic properties of limits and things like that, and talk about a strategy for approaching different kinds of problems. But you go big or you go home, and we're going to both go big and go home with this topic here. It's called infinite limits and limits at infinity. So for our purpose, infinity will be an answer that is meaningful to us. It doesn't make sense on a number line or as a numerical value, but it does describe a certain kind of behavior that we'll want to know is happening if it does happen, right? Something increasing or decreasing without bound is an important thing to pay attention to. And so we can capture that idea with the idea of infinity. So if we consider something like the limit as x approaches a of our function, let's call that L. So we can say the limit as x approaches a of this function is L, meaning L is the y value we're getting close to when our x value gets close to a, right? And so here's the definition. If L is plus or minus infinity, call the above an infinite limit. If the a itself is plus or minus infinity, it is called a limit at infinity. So that's an example here. Consider the function, a very important function, y equals e to the x. We know what the graph of that looks like. Sorry, that passes through 1. Gets closer and closer to the x-axis as we go off to that way. And so now, let's look at these guys. Limit as x approaches infinity, and limit as x approaches minus infinity of this function. So I'm taking two limits at infinity. The x values are at infinity. And I want to kind of figure out what are the y values doing. What would you think the first one is going to be? The infinity would be the only response that could work. You could never say a number. You can never say y equals 5 trillion because eventually it will pass that, right? No matter what y value you tell me, eventually the function gets bigger. You tell me that, it gets bigger. You tell me that, it gets bigger. It doesn't make sense to give a number as the answer. But it is an important behavior. This guy's just skyrocketing up, right? It's growing super fast without bound. That's kind of something I'd want to know is happening or not, depending on the context. And so infinity seems to be the only idea that can capture such a behavior. Right? So as x is going to infinity, meaning you're going to the right, far, far to the right. You go a trillion miles to the right, you keep going, you never stop. You keep going to the right, the graph will keep going up and up and up, and that is described as the graph going to infinity. Okay. If you look at it from x approaches negative infinity, same idea. You go far to the left, just keep going far, far, just keep going forever. What is the y value approaching? 0. So that one actually does give us a number. One thing I do want you to appreciate here is that e to the x never actually is the value 0. E is a positive number. The power, no matter what power you raise a positive number to, you can never actually output the number 0 exactly. But again, limits care about getting close to something. We're inching and inching closer and closer to 0. We might never actually get there, but the limit doesn't care. That is the value of the limit. because if I pick any other number, eventually I get smaller than that. And we have a couple minutes, so we can consider this example. Example that was brought up. Look at the y equals 1 over x. So we look at something like that. So this is a limit at infinity that is also an infinite limit. This is a limit at infinity but is not an infinite limit. Let's look at this guy, the limit as x approaches 0 from the left of 1 over x. The limit as x approaches 0 from the right of 1 over x. And the limit as x approaches 0 of 1 over x. Now, one thing I want you to know is we cannot actually plug in 0 here, obviously. Another thing I want you to notice is, unlike our second example, I couldn't factor stuff and cancel that x, right? So I'm unable to factor, I'm unable to cancel, right? And so I'm kind of stuck with the formula in the way it is, right? So what I can do now is that I can instead look at the graph, right? One option would be to just keep plugging in numbers closer and closer to 0 and see what happens. You'll notice that all your y values are just getting larger and larger and larger and larger, right? But another way to approach this is, I know the graph of 1 over x. It's one of those things I know what the graph looks like. So if I'm approaching 0 and I'm on this function on the left, and I think, what is happening to the y values? I keep going down and down and down and down and down forever. I'll never actually hit 0, of course, but as I get closer to 0, my y values will go down. They will decrease without bound. They will go to negative infinity. On the other hand, if I'm on the right side and I'm approaching this, the y values will keep going up. And I can say that this is positive infinity. And now, because I know the one-sided limits, they actually exist, I can talk about the overall limit. Clearly, if a large positive number and a large negative number are not the same, so I can say overall the limit here does not exist. So we'll stop there. Those are a lot of ideas for you guys to mull over until we hit the limits again. I do have things to give back to you, so hold on a second and then we'll